Hello everyone. In this video we would basically extend our knowledge on the decision trees, and we would also see how to get rid of the overfitting problem of decision trees about which we talked about in our previous video. So by the end of this video you will be able to understand the concept of Gini index, learn about the CART algorithm, understand various stopping criteria, learn about also pruning in decision trees. So this is a measure which would just help us to get rid of the overfitting problem to some extent. And also you must note that uh, in this video and in all the previous videos as well as the upcoming videos, I will put these downloadable slides as PDFs format on a Google Drive link. So let's just start. So we define a concept called Gini index. So it calculates the amount of probability of a specific feature that is classified incorrectly when selected randomly. If all the features elements are linked with a single class, so it can be called pure. I explained it in the previous video about the decision tree when a node can be called pure. So this Gini index is the measure of purity of a node. So this is 1 minus sum of the squares of all the probabilities of the classes at a particular node. So a low Gini index means purer node, and hence it is more desirable. So our objective of splitting in the decision trees can also be based on minimizing the Gini index of each and every node. That is, we are going towards more and more purer nodes. So if suppose let's say our node consists of 50 elements of 3 classes respectively. So let us this be Iris, Setosa and Virginica of this Iris dataset. So our Gini index will be, so what is the probability of the first class is 1 by 3, 50 by 150. Next class is 1 by 3, 1, and the third class is also 1 by 3. So we do Gini index 1 minus summation of square of the probability. So 1 minus 1 by 9 minus 1 by 9 3 times. So it is basically 1 minus 1 by 3, which reduces to 2 by 3, which is 0.667. So the resultant Gini index would be the weighted average of both the nodes. So let's say we take a decision out of which we split 0, 50, 0, and we also split it in this way. So here is Gini index is 0 because it is a pure node, you can see it, and the Gini index is 0.5. You can just calculate the probability. The probability of the middle class is 0, the second class is 1 by 2, and the next class is also 1 by 2. So our Gini index will be 1 minus 1 by 4 minus 1 by 4, which will be basically 0.5. So the resulting Gini index is the weighted average. So 50 by 150 is the weight of this class multiplied by 0, and 100 by 150 is the weight of this class, this node whose Gini index is 0.5. So the resulting Gini index is something like this. So there is something known as CART algorithm, classification and regression trees. So what it does basically, it splits the data into two subsets using a single feature k and threshold tk. Example, petal length less than 2.45. This is done recursively for each node. So what does this CART algorithm says? We had a feature on which we can split, and if our feature is continuous like the length of a petal, we will keep certain benchmarks like 0.25, 2.45 meters of petal length less. So in the decision tree we will ask, is petal length less than 2.45 meter? If yes, we will split on one side. If no, we will split on the other side. Similarly, k and tk are chosen in such a way that they produce the purest subset weighted by their size. So Gini index must be least in such a way k and tk are chooses. The objective being to minimize the cost function, which is the weighted mean of the Gini index. So in this CART algorithm, the cost function is the resultant Gini index or the weighted mean of the Gini index. So we need to apply some stopping criteria, or it will lead to overfitting. The decision tree will keep on splitting until it gives purest node basically. So we need some stopping criteria. So decision tree may frequently lead to overfitting, therefore we require more stopping criteria. One possible way is to somehow choose a max depth beyond which we don't need to split. So what is the depth of a decision tree? The number of splits we do, and the second level, third level we reach. Suppose after first split we reach the second level, after second split we reach the third level, and so on. Suppose we can just fix a maximum depth beyond which we don't need to split. So this can be a stopping criteria. We can also stop when we don't get significant improvement in scores. So in the previous video you saw that with each split you get some improvement in the score. So there was something 80% accuracy, which after splitting became 82% accuracy, if you recall those interview data set or something like that, interview call. So in that decision tree we get so in if in our decision tree we don't get significant improvement in scores after a certain point, we can stop at that point. There are other hyperparameters like minimum sample split, minimum samples leaves, minimum weighted fraction. So you can go through this in the documentation. So I will provide the link of the documentation also. So pruning is something you need to understand to prevent overfitting. So what it does basically, so let us plot the graph between error and complexity of our decision tree. So how the more complex our decision trees, the more number of leaf nodes we have, and the training accuracy increase, like the training error decreases. So the more complex data set, we will have more training accuracy and less training error. But for testing, for certain points after splitting we get a gain in accuracy and then the error will start increasing. So we fix some point above which we don't want to go and don't want to basically increase the error of our testing dataset. We sacrifice some of the amount. So that is basically our pruning point. So our cost function after pruning will give us error of train plus lambda into n of t. This n of t signifies the number of leaf nodes in our decision tree, and that is basically a measure of how complex our decision tree is. We select a suitable lambda and check our cost function before and after pruning. If after pruning the cost reduces, then we would get rid of the split. So whether to get rid of the split, so pruning basically means to cut the leaves of a decision, leaves of a tree. So its technical meaning is to cut the leaf. So whether we want to get rid of the split or not, we can do that by giving a suitable lambda and checking our cost function before and after pruning. If the after pruning, after cutting the split, the cost function reduces, then we will get rid of the split. So what it actually means, we will understand it clearly with an example. So here it is also a type of regularization, you can say. Here low means overfitting and high lambda means underfitting. Because of the similar regions I have stated in the regularization concept, if we are increasing lambda, we are more focusing on just the complexity. So it will be underfitting and the reverse will be overfitting. So with this example we will see. So we have our cost function, which is error plus lambda into n of t. So let us take the error function to be the number of misclassified classes. So our error function may be many other things, but for simplicity here, let us take the number of misclassified stuffs as the error function. So now class, and let us assume lambda equals to 1.5. So let's say we have this complex decision tree. This is the split, this is another split, and there are a lot of split. So first you count how many number of leaf nodes are there. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 leaves and 0 error before pruning. If we notice that each of the leaves are pure, each of the leaves are pure, there is no ambiguity, there is no requirement of any majority vote. So each of the leaves are pure. So initially we have error 0, and but we have the lambda equals to 1.5 and the complexity is 10. So that is the number of leaves basically. So we have the cost of this decision tree is 15. But after pruning, let's say we are cutting out this split. If cutting out this split means we are not classifying this as 1 yes and 2 no, we are just ending it here. So instead of 2 leaf nodes, we are now having 1 leaf nodes. So after pruning, we have 9 leaves and 1 error. So one value of yes, we are doing majority vote and telling it as no. So we are committing one error. So error is 1 and the number of leaves is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number of leaves are 9. So the cost function is 1 plus 9 into 1.5, which is basically 14.5. So you see here, after pruning, after cutting out this tree, even after committing an error, we are ending up in reducing our cost function, which is favorable. Since our final cost is less, so we would here do pruning and get rid of the split basically. This is the concept of pruning. So in the next video, we will see how to apply this decision tree on sklearn, and our next video will be probably on some decision tree application. Also, don't forget to download the slides from the description link of Google Drive PDF. Till then, thanks a lot.